session is all about um, basically technology innovations in order to make the refining and petrochemical business Atmanirbhar. So, and there are different topics people will talk about. Some will talk about modeling and a digital twin. Others will talk about single step process for DME. Some others will talk about dewaxing technology. So, with that, we can have the first speaker.
Good morning, everyone. As Dr. Mitra mentioned, this is one of the last session, but not the least. This is one of the most important session. So without further ado, I would request Mr. Naresh Kottari to share the entire thing about the propane dewaxing and how that can actually drive the operational efficiency. So over to you.
Good morning, sir. Good afternoon to all of you. So thank you for the IW team for giving us an opportunity to talk one of the additive that we developed at our R&D. So today I'm going to talk about brief developmental strategy and how we have taken this from the laboratory to the field level of an important additive in our Mumbai refinery. So the content of the presentation is I would like to give you one or two slides about where it is useful and why it is required, and then I will slightly touch it upon how did we arrive this formulation both from the in vivo as well as from the molecular modeling studies as well as from the laboratory, and then going back and forth to achieve the desired formulation. So once we completed the modeling, how do we do in the commercial trials, and finally where it can be applied. So when we look at the chemistry of the lube oil, as we are aware, the petroleum industry, whether it is from heavy or lighter crude, has the all components like N-paraffins, isoparaffins, cyclic and aromatic and so on. But by the virtue of the lubricant properties, some of these components are not desirable. For example, N-paraffins are not desirable due to their high pour point, and aromatics are not desirable due to their lower thermal and oxidation stability. So what the group 1 lube oil production does, they remove these least desirable components through the physical methods. For example, aromatics they remove through some extraction process, waxes they remove through the dewaxing. And sometimes it may be necessary to modify the components to have a better color and other properties. So this is the typical block diagram of our Mumbai refinery. So when we look at this flow diagram, so what we do, we basically take out the vacuum distillation cuts, and various cuts are separately subjected to something called SEU, which is to remove the aromatics, and then basically propane dewaxing, which is to remove the wax. So the additive that I am going to talk about is particularly based on this unit operation. And as we can see here, these units are operated in a various modes depending on viscosity, starting from 70 N to all the way to 1300, or also known as the breadstock. Especially the solvent dewaxing aid, which I mentioned in a previous slide. This is very important unit, and then this unit operation may not be viable without the intervention of this dewaxing aid. So what it does, if you look at the right hand side diagram, so it basically the aim is to separate the wax. So we take the advantage of the high pour point of the wax by chilling the entire mixture. So thereby this wax will get separated out, and then we filter to get the base oil. But if you do as such without any nucleating or directing agent, we get the all different shapes. So the filtration is difficult because of the trap of the oil in the wax. Whereas if you use a dewaxing gate, that means basically a controlled directed crystal growth, what happens is, so depending on the polymer, we can actually get the spherical shape of the wax crystals. Thereby, it allows the filtration of the base oil much more effectively. So the key is the formation of the spherical uniform crystal formation. Another important factor for our Mumbai refinery is this particular additive is not available in India to sustain our operation, and then we are depending on the imported, that too from a single vendor. So just to show you how basically when we are dependent on one party, so how the price will vary, you can see from starting from 2018 to 2023, so this almost become like 40% more than what it is in 2019. So this is even higher even if you take into the account of even the typical chemical prices. So prior to our development, we have also tried more than 12 different types of additives from Indian as well as the imported vendors, but none of them was successful. So that kind of triggered our intervention in the indigenous development of this imported additive for our sustainable Mumbai refinery operation. So how did we start it? Because we are little bit aware of what the additive is doing and what kind of chemistry is used. So we have started with the molecular modeling, because it's very difficult to make so many additives and test in a commercial enterprise. So we have started from the modeling, and then based on modeling we have designed the experiments. So once we have come to kind of one molecular structure, then we have made the structure, and then we did perform evaluation. If this is not right, then we went back to modeling. So this is basically cycle to get the desired output. And finally we did the multi-ton scale up once we identify the right formulation. So if you look at the novelty aspect of what we have incorporated, see, as I shown in the introduction slide, because of the various grades of the viscosity, the alkyl chain will vary within the wax. So what we have done, we have incorporated various tunability in the polymer itself. So that means I can incorporate whatever the alkyl chain that I want, and aromatic co-monomer is also plays an important role because of solubility. The key novelty is the small amount of cross-linker, which I am going to explain little more detail in the next two slides. So what it does, if you look at the same length polymer, and then if you put a cross-linker in between, and you do a molecular dynamics using hexane or similar solvents as a background medium, when we take the frames of the dynamics, we can see this kind of the linear polymer. Whereas if you put a cross-linker, because of this constraint, it is try to achieve the spherical shape. That means basically the 3D-dimensional architecture of the polymer, it's here more or less leading to spherical globular conformation. Why it is very important? Basically, we know that the spherical wax crystals are very easy for smooth filtration. So we wanted to have nucleating agent also in the spherical shape. So just to illustrate the effect of cross-linker, we have taken the same molecular weight polymer, one with the cross-linker and one with the cross-linker. As we can see, the filtration rate is nothing but the efficiency. As we can see, the polymer with the cross-linker has shown 1/4 of the time. That's basically indicating the efficiency or the novelty of our own concept. So once we have achieved this, in fact, we are not the first one to do the spherical conformation. Already the commercially available polymers achieve the same thing by having the ultra high molecular weight polymer. So basically, when you coil them, it also achieves the same thing. But with the chemical intervention, we are able to achieve the same thing in much more lower molecular weight, which translates into a lower dosage. So this is the lab scale evolution. I would like to focus on this particular thing, which is the yield compared to the imported one, and then we are almost like a 3 or 2% higher than the commercial chemical. In fact, the filtration time also is better, indicating that our concept is really working well even in the laboratory thing. So once we have completed the laboratory thing, we have taken a field trial. In fact, as I speak, this is being continuously used in our refinery. As on date, more than 300 metric tons is produced. So if you look at the field trial data, one of the 150 N feed, for the commercial chemical with the 3 filters, we were able to go up to maximum 45. Whereas our dewaxing aid with the 2 filters are online, we were able to go up to 70 with the lower dose. So that means the filtration efficiency is much more high. So previously our refinery, though it is a single imported chemical, they used to face some difficulties with the lumps formation, which we have eliminated with our indigenous additive. So by this way, it is we are able to save a lot of not only the import money, also the performance also significantly improved. So when we look at the monetary benefit, the cost, as I said in the first slide, so ours was like a 45 percentage lower than the commercial chemicals. We have indigenous, the one of the important additive. In fact, during COVID time, we have faced a lot of constraints because lack of the supply. By tuning the parameters, we can even enhance the performance. So we are discussed with the CPCL to take a trial and then basically try to see whether we can supply to the another refinery which is right now using a dewaxing aid. So during the modeling studies, we have learned a lot about this wax modification. So the same concepts were applied in the PPD production. Basically, we have ready-made available data with us right now. So we wanted to know any of the wax modification, we know what polymer backbone to be taken. So by that way, we have made a PPD, and the performance of the PPD is also like better in comparison with the field. As you can see with the commercial, it was 12 degrees centigrade, whereas with our own 21 degrees centigrade drop for the same dosage. And another interesting aspect that we are looking into this edible oil industry in India, it is highly unorganized sector. So they also do this dewaxing aid to improve the flowability of the vegetable oils. Exactly same concept. So we would like to see whether it can be applicable, and then we are also trying to see some laboratory scale evaluation of the same. So this particular concept that whatever explained in the modeling was patented in two patents. Some of them are already granted. Prior to even patent grant, before we take commercial trials, we also obtained the freedom to operate. So as to eliminate infringing of any of the known IP rights. So that brings me to conclusion slide. So as I explained, with the careful designing of the modeling, so what we have done, basically we have kind of used our cross-linking chemistry. So while doing that, what we have done, basically, since anyway we are stitching out from the very basic monomer, we were able to attach the tunable alkyl chain. So this is very important as we are dealing with the various types of viscosity. That means basically various viscosity grade alkyl chain length is different. So right now we were able to offer the solution, any of the wax modification, depending on the alkyl chain in the feed, we can design a polymer. So this concept from the laboratory was taken to kind of refinery field level, and in the beginning we also faced some difficulties based on basically one of the reason is there is no absolute laboratory standard method which mimics the refinery plant operation. However, we have overcome that, and then from past 1.5 year, our refinery is exclusively using for our own additive only till date. I mean, this financial year alone, we have made around 250 metric ton. That means, so its annual demand is approximately about 300 tons. So as I shown, because of the high throughput, we can actually also get some monetary benefit while producing more base oil. Because this is designed from the very fundamental building blocks, and there are similar industries use this dewaxing chemistry. One of them I have shown, that is basically the vegetable oil dewaxing to enhance the flow rate. So that also we were now trying to discuss with few people to demonstrate the concept and then to take it to a next level. So that brings me to the conclusion. This is my last slide. And finally, I'd like to thank the IEW for giving me an opportunity, and also thank the audience for patient listening. If any questions are there, I'll be very happy to answer. Thank you.
Thanks a lot, Naresh. Really appreciate, and in fact, we are also looking forward to the promise of this application in the further industry. So it's a good, everyone is going to look for that. Thanks for it. With that, I'll request Mr. Mahesh. Can you please come? Thanks a lot.
Thank you, sir.
Very good morning to ladies and gentlemen. Last day, last session. So I could see good crowd to see. At least I have to thank the team who could join and see our presentation. I would like to take the opportunity to thank IEW as well as my EAL team, and then some of the seniors are available here. So it will be good sharing of technical papers here. So the contents, I just want to say, this overview of refinery and petrochemical complexes, whatever EL did, that I am going to cover it up. And then whatever the refinery and petrochemical corresponding control system configuration, and we have achieved one single network control system for the latest job. And while implementing, what are all the integration strategies we have adopted, as well as the implementation challenges I would like to discuss. So EAL, everybody knows, we are into engineering consultancy company, and the following are our major areas, that is petroleum refining, petrochemicals, chemicals, fertilizers, and now we are into infrastructure and urban development also. Any oil and gas, total 3 streams are there, upstream, midstream and downstream, but I am going to cover the downstream part where refinery and petrochemicals are involved. So the overview of refining industry in India, almost 23 refineries across the India with both public and private sectors, and we are exporting around 40 MMT of petroleum products. So such a huge production of 265 million metric tons, automation is imperative. It should be of the state of the art. So the major units, if you see refinery, that is process units will be there, steam and power generation is required, followed by offsites, utilities and tankages. So these are all the various oil refining process over the timelines. These are all the topping refinery, skimming refinery. Now we are into crude oil to chemicals. That is integrated refinery, lubes refinery. Even earlier my speaker talked about some lubes refinery also in BPCL. The oil refining profitability over the years, based on gross margin versus investment cost, if you go for petrochemical integration, then only you will have a high profitability. That's why most of the units, refinery complexes are coming up with integrated petrochemical. This is the schematic of oil refinery. I don't want to discuss in front of HPCL and BPCL regarding the basic components. These are all the inlet and these are all the products what we get. So if you go through the basic refining process, the primary refinery unit CDVDU, followed by the molecular rearrangement and combination, that is CCR, iso, sometimes alkylation is also added. And then if you go for molecular cracking, then FCCU, DCU, and then if you want to remove the contamination, then DHDT, NHT, KHT. And then followed by, you get all the auxiliaries and utilities. Why I listed all the basic units is, so for individual unit, you need an individual control system to operate. So apart from the units, you need the other facilities also, that is offsite facilities, product dispatch, as well as utility systems. So these are all the facilities also required for a complete refinery to be operated from the main control room. So why integration? So if you integrate with Petchem, the operation will minimize the cost and optimize the product distribution. Whatever is the demand in the product market, accordingly you can optimize the process and you get the maximum benefit of the materials. Then supply chain optimization is also always controlled, and then feedstock flexibility you will have, which feedstock is required and what is the product to be given. So let us go with the control system part now. This is the basic control system for refinery configuration. One is the CCR is the main control room with connected to various SRRs. This is only with respect to refinery I have listed. So other three control rooms are required, anyhow, water block control room and power plant control room. These are all the basic configuration of a refinery control system. If you go for standalone refinery and petrochemical, you need two different setup. At the same time, you have a separate CCR with respect to petrochemical and refinery. Nowadays, this is another control system for petrochemical unit, but here you could see, apart from refinery unit, bagging control room is added because of handling of the solid particles, that is PP, LLDP, that is the product. For that also you require a separate control room. So apart from the refinery, this bagging control room is also added. If you further see the latest MRPL, HMEL and Dangote refinery and all, they have added PP unit. So along with the main network, I am getting added to SRR PP also, so that in the main network, you will be able to control the entire plant. Here the challenge. If I have an integrated refinery and petrochemical, you see the control room part, that is RMCR refinery control room, then petrochemical control room, and then other control rooms are anyhow listed. So the number of networks, number of domains, all getting added. So this is the area, if you integrate it, and what is the maximum efficiency with the safety integrity we can achieve. This is the topic I am going to discuss. So the integrated control system, if you see, the number of input output, that is around 1.5 lakhs. If you go for refinery, it will be around 60K, and then if you go with separate petrochemical, it is 40K. If you add power plant also, so the number of IOs we need to manage is around 1.5 lakhs. But the control system cabinets, you see the quantity, that is 1500. 1500 cabinets in a single stage project. You need a lot of efforts for the optimum performance of the overall complex. The number of SRR saturated rack rooms has just got doubled, and then the software domains with respect to each unit, that is also got doubled. And then the number of operator console, if you see the 150 consoles in a control room, such a huge number. So if you go for integration, then you will get the process demands, that is petrochemical unit integration with your refinery unit. So whatever these are all the demands we received during our control system integration. Whatever is hydrogen is generated from DFCU, that will be utilized for the overall complex. But DFCU will be started with the basic hydrogen requirement. That will be shifted from my primary refinery unit. And then once the DFCU is stabilized, then HGU unit will be operated with 88% capacity. Rest I will manage from 18%. This is the optimization I am getting with respect to hydrogen production. And then for the startup hydrogen, I will shift it from DHDD to DFCU block. So these two units integration from petrochemical to refinery, if I have a single network control system, whatever the process demands, it will be implemented on the same network, and then I am getting the system implemented without any hassles. If you see the steam and power demands, this is the example I had given. In our plant, around 5 number of GTGs and 4 CFBCs and 2 boilers. This is the overall requirement of the entire complex, but only 2 STGs and CFBCs are required for my power block. If that trips, then I need to manage the steam with respect to overall the complex. For that, steam shedding and load shedding will be easily managed through a single network control system. This is a just schematic I have displayed here. And then next comes the final product. If you won't give a proper blending on the same network, and then whatever the input requirement changes, then based on the market demands, with the same blending control system, we can manage the requirement from the operation group. So nowadays, the rigid as well as the stringent requirements with respect to product quality. So these are all the challenges in blending we could manage with the same single network control system. So these are all the basic requirements of a blending control system part. And then these are all the blending demands. The 13 streams, this is the very high figure with respect to blending system, as well as we need to produce both MS regular as well as MS premium. With both the same system, based on the market demand, that system should be capable to manage both MS regular as well as MS premium. That is without any lot of turn down wastage. So the blending ratio controller is also we have considered as a part of the same control system. These are the challenges I would like to highlight. One is always the demand operation from a single control system, that is both petrochemical and refinery. If you accommodate 150 consoles, even this IEW hall will be our control room. So such a big control room, it is not possible to manage. That is the demand from the operation group or the client. And the number of nodes and domains, if you see, it will more than 20 or 16 was the requirement. With future addition, if you go for it, that is also challenge with respect to nodes and domain limitation with respect to single control system. But whenever I choose any supplier, I should have the minimum basic reference. If it is 150 IOs, I should have the supplier earlier, he would have executed 50,000 IOs. So that is also a very big challenge to get the right supplier to implement the entire control system with all complexities. And then if you are implementing petrochemical separately and refinery separately with a gap of some years, then you will have a different philosophy. But in this case, uniform philosophy is the requirement with respect to the entire complex. So the petrochemical group will be having different method of, because solid handling is there, but refinery is mostly in different type of handling. So the uniform philosophy adoption was the biggest challenge we could face it. Then complex control philosophy, that is whatever the process demands, that with various scenarios, it needs to be understood, and then it should be adopted in such a way that whatever the final outcome is possible. Nowadays, cyber security is the biggest challenge. So as well as the network switching, if you are having 1,000 nodes and 150 operator station, as well as the cyber security is also a biggest challenge. Then to implement such a big job, the logistics and manpower at the same time, you have to take care of the entire implementation to get the final output. I hope I have covered everything. Thank you very much. Thank you, sir.
Thank you, Mahesh. Very insightful session. Anybody, any question for Mahesh?
No, we cut out the question.
Okay. So I'll now request Mr. Rakesh.
Good afternoon, one and all. I'll be discussing my topic on the DME production technology demonstration. So before moving forward, I would like to thank the IW for selecting my paper. At the same time, I would like to acknowledge my organization for allowing me to share my work. And also, how could I forget my colleagues who has worked along with me during the project. So with that, I will be starting my presentation. For a quick glance, a DME is nothing but is called as a dimethyl ether, which is having an ether bond between the carbon molecules. As a result of which, on combustion, it will be a clean fuel to burn. It won't leave any soot or any other material will be left out. So that's why it is called as a clean fuel as well. As a result of which, it can substitute the LPG and the conventional diesel as well. So if you see the properties or the characteristics of it, it liquefies at around 7 bar pressure. So which is close to like the LPG usage itself, we can use the existing infrastructures. When we compare with the diesel, it has a C10 number as close as the diesel itself. So that is one of the major reasons for the fuel substitutions. It is also used as an aerosol propellant because most of the propellant requirements are being fulfilled by butane and propane, which is from the LPG derived molecules only. And then it has an industrial use as a solvent as well. So this is what is the demand and the requirement of the DME. So moving further, this can be produced in two ways, which is called as an indirect and a direct pathway. So indirect is what till date the commercial DME production is being followed on, which involves two steps. One is the methanol formation and another is the methanol dehydration. So the syngas in both the systems, both the technologies need to be derived from either from the natural gas, coal, biomass, or any other substitutes. Whereas conventionally, it is like 50% of the syngas demand is being met from the natural gas itself. When you go for the direct DME, so we'll be using a hybrid catalyst, which processes the methanol which is formed during the reaction itself into the DME. So as a result of which the kinetics shifts towards the methanol formation onto the right-hand side, and then as it is being immediately consumed into the DME, So it makes the conversions much more better. So if you look at the market demand, the global demand of the DME is close to 18 KTPD, whereas in the Indian market it is very low. It's close to 2 TPD per annum. I mean 2 TPD demand is there. So this is one of the reasons why it is not such a not lucrative within India, and let's see why it is not even lucrative and how we can make it lucrative also. So the market demand distribution is like globally it is being used in LPG blending, followed by the aerosol propellant applications, and then the transportation fuel, which is along with the diesel as a substitutes. Whereas if you see the Indian market, because as the LPG costs and the diesel costs are so less, which it cannot compete with, so obviously the majority of the share is going to the aerosol propellant itself, followed by the industry and the academic applications, and among which the major share is taken by the West and Central India, which is close to 83%. So which are the areas you can say like the optimum place or the location where we can set up the DME production facilities if required, followed by the North India. And the DME pricing, now you can see the difference. It is being sold at almost like 94% of the DME which you are getting is being bought out at 722 1,430 rupees per kg, which is a very big number when compared to the conventional LPG and the diesel figures. So moving further, what is the chemistry behind it and how we have developed it? So during the developmental phase, we have a chemistry phase, which is at the laboratory level, followed by a technology level, where we will be developing into the technology with the works on the pilot plants, the studies on the reactors and these things. And finally, we move towards the economics. Though the economics looks at the last part, but it need to be followed at each and every level as well. And in my presentation, I have covered how it can be taken care as well. So these are the catalysts, few of the catalysts which we have developed, and the results are already reported in Journal of Catalysis, so which can be referred further. One of the best catalyst with highest conversion and highest selectivity. This is being chosen for our commercial demonstration plant. And when it comes to the reactor development, this is the exothermic reactor system, exothermic system. So the reactor should be capable of removing the heat. So multi-tubular reactor system was developed by us in collaboration with CSIRO Australia. So this we are planning to use in this one. As far as the tube sizing and these things are concerned, which is a major challenge for us, so that we have followed by developing an isothermal reactor. So wherein we perform the studies of the temperature profile distribution within the reactor itself. So which has got the complete radial and axial profiles, like a 5x5 matrix we will be getting. So accordingly, this helps us in identifying the right size of the tube which need to be used for the reactors, so that the temperature shoot up and these things can be avoided. Based on all these laboratory informations and these things, we went up with a technique for developing a technology package, which is a BDEP package, for setting up a 10 TPD brownfield plant. Why I call it as a brownfield is because we want to set up this in one of our existing refinery where we have a syngas. So the land investments and these things won't be there, which conventionally have with the greenfield projects. And the capex requirement is as low as 40 crores itself, so which looks to be promising for us to move ahead. And moving further, we have also developed an in-house Aspen flowsheet, a detailed one. The basic objective of this Aspen flowsheet is, one is for the modeling optimization. At the same time, we use it the same for cost estimation as well. I mean, the same simulation file we have used onto the Aspen process economic analyzer, wherein we were able to evaluate the capex numbers, the operating costs, and everything. And we are happy to share that these were very close to the BDEP figures. I mean, the capex requirement which we got it from the Aspen is actually matching very close to the demonstration, the BDEP package numbers. So there is an economic model, we felt like there will be a need of this one, because we need to play with a lot many parameters like the capacity at which the plant will be viable, the raw material cost, the product cost. So having multiple strings, it would be very much difficult to identify the right plant sizing as well as the raw material costing. So for which we have developed an economic model which works on the principles of the operating ratios. Operating ratio is nothing but operating cost by the value of the products, which means like when this is 1, you are in a no profit, no loss kind of a scenario. So the lower the operating ratio is, the better your margins will be. The higher it is, the lesser the viability of the project turns to be. So we have developed 3 correlations. Each correlation has a significant application as well, because the OR1 uses only the raw material cost, which can be used during the chemistry or the laboratory phase development. And if you still find like your ORs are pretty much lesser than 1, you can go ahead, or else you need to tune at your chemistry level itself. wherein you need to increase your conversions and selectivities, followed by the equipment cost, which comes at the technology level, followed by the capex level, I mean the operating three ratios. So as the information more and more is available with you, you can switch to using the appropriate correlations. And as said, like the accuracies will be proportionally increasing. I mean the highest accuracy will obviously be with the operating ratios of 3. So you can see here, this is the error plot among the various equations which we have developed. So you can see like whatever the orange are there, which are the equation 3, are pretty much close to the NPL line, which is the diagonal one. So the values are pretty much close to that. So that's how the accuracies are pretty much closer. And if you ask me about the reliability in the decision making, if your operating range is within 0.7 to 1.3, you can say like the reliability of the model is more than 95% itself. Though you see the bigger numbers over here, but these are unfortunately onto the extreme ends of the operating ratios, maybe like 0.2 or 2, wherein the decision is directly like there is no need of any error which need to be considered over there. We have also performed the plant sensitivity sizing on which plant size gives us a decent figures in terms of economics. So considering at 20% of a market share if you want to capture, and if I'm setting up a 9 TPD plant, then it's like even by the end of the life of the plant itself, I will not be using its 100% capacity. But however, if I reduce my plant size to 4.5 TPD, and if I could push to sell the product at 50% of the market share, because this is 100% import as on date, so as an first mover advantage, we can target up to 50% capturing the market share. So wherein by 2029 itself, we could be running our plant at a full capacity. But however, after that, we will be losing the market share because my plant capacity is already full. So it's like a trade-off, like at that particular instance, we can take a call accordingly, like what would be the plant size which we need to take care. And similarly, if you still target for a 20% market share itself, then we can even go for a 3 TPD plant itself, which will be having its full capacity operation at by 2031 itself. And then if you see about the returns, on an average price, though the price of the DME is very high in the market, so if I consider it as an average selling price of 600 rupees per kg, considering 20% of a market share, I can sell, my IRRs are as good as 35%. Usually it's like beyond 15 or 20% itself looks to be very much lucrative. But within this much of a small plant itself also, we are getting almost like 35% of an IRR. And when it comes to the cost, it's obvious that as we increase our production and the market share, we can sell the product at a lower rate. So that's why the other graph is in the vice versa. And we can bring down the cost up to 270 rupees per kg. However, these are just like the calculated numbers. And when we work these things on the actual demonstration plant level, the numbers may even come down. So the substitution potential, this is one part of it. The other picture which I was discussing, like why this cannot substitute the conventional fuels, is the energy the unit cost of the energy is very high for the DME when compared to the conventional LPG and diesels. So it's like for the conventional diesel, which is currently at 79 rupees refinery transfer price. If I need to substitute with the DME, I need to sell my DME at 54 rupees. It's like I need to substantially downgrade the value of the product from 600 to 54 rupees. Which anybody will not be doing in the business scenario. So that could be one of the reasons why it is not that much lucrative. But yes, in future, as the prices increases, the curve shifts towards the the bottom of this LPG and the DME energy pricing. So obviously DME can replace that respective of these things. We have also filed a couple of patents on this. One is on the entire separation technology, because it needs cryogenics and these things, but the separation technology which we are referring to doesn't need any cryogenics. That is one of the advantages why we are able to get a better pricing. And another is a reactor configuration itself, wherein we proposed a reactive distillation kind of a configuration for this one. The demonstration plant which we are planning to come up with, we are trying to valorize both of the patents over there, so that whichever gives us the best economics, we can move ahead with that particular technology. And the major challenges in front of us is like we need to reduce the production cost, so as to produce green DME, because whatever the hydrogen is being required in the syngas, we need to substitute that with the hydrogen, which is the green hydrogen. So the cost of the green hydrogen also plays a crucial role in the pricing of this one. So that would be the challenging part for us to reduce the cost of green DME, and furthermore selling it as a premium fuel, because the cost of the DME and the cost of the fuel, there is a much price gap between these two. So we need to bridge this gap so that it can be sold as accepted as a premium fuel. And what we've at the BPCL planning further is like to first of all have a reactor demonstration technology, so as to demonstrate whatever the findings and the developments we have made. Set up a demo plant, which should meet the market demands as well, because the market size is also small. And then go for the process optimization and tuning of these parameters. And then we will be planning to do the scale up as per the market demand in the future. So I would be happy to answer any questions or anything. Thank you.
Very insightful. Thank you. Much appreciated. Can I request Dipankar to please come?
Hi, good afternoon, everyone, and thanks. I would like to thank the IW for giving us this opportunity, and also I would like to thank the session chairs and all the audiences presented here. So today, myself, Dipankar Mitra from KBC Advanced Technology, will be presenting on the advanced analytics usage in the refinery and petrochemical units. So these are the contents of my presentation. So basically we'll touch upon the attributes of the advanced analytics. We'll also see what are the objectives of deploying this advanced analytics and the value proposition it has, and some of the tools we use to develop this advanced analysis. And then briefly we'll touch upon the ideas of digital twin and its applications, and similarly on the dynamic real-time optimizers and integration with AI ML, how these tools can be enhanced. So first on the attributes, so this advanced analytics has been an evolving field, and since last few years it has been discussed and also deployed. Some of the attributes we have listed below. So what we mean by advanced analytics? It is like autonomous or semi-autonomous analysis of data or content using sophisticated techniques and tools. Another advanced analytics aspect is typically these are beyond the typical business and intelligence BI, what we call, and also they are used to discover deeper insight and to make predictions or generate recommendations. So what are the typical objectives? What we see on the client sides is that people, refineries or petrochemical units wants to improve or sustain their profitability. That is one of the major stay. And also there is a drive to reduce energy consumption. There is some of the requirements on the monitoring of reliability aspects and to minimize energy emissions. So I think these are the predominant reasons people deploy the advanced analytics. So these are some of the typical value propositions we have for the deployment of the advanced analytics. One is on the visualization side. So basically it improves, make the KPIs available, and there are some of the KPIs which are intrinsic. I will touch upon later also. So like column flooding or the efficiency calculation or say cyclone velocity, etc. Things like that, those are not directly measurable. Some are measurable. Apart from that, these tools provide a visibility of the information across the organization, and they drive the collaboration. So once you have the visibility and the ability to calculate a lot of data, that drives the collaboration in the organization. Data reconciliation using first elemental balances also adds a lot of value. There is another segment on the LP model assurance. So these tools are being used, deployed, where we can basically see the performance of the LP against the actual, so it ensures the trustworthiness, and also it, as the LP model upkeeping is well, so it provides optimum operating target. So basically a good planning, and that good planning results to enhance scheduling and reduction in the operating cost reduction. Now there is another part these tools play is on the process simulation model health assurance. So they basically it can track the performance of the process models, and also these process models are being used for various purposes by the engineers for what if study or any other configuration study or anything. So this upkeeping is very important. So optimum utilization of the units and equipments is also being ensured once you have a good set of model which are reliable, and then drives the opportunity identification and implementation. On his own, analytics may or may not drive the opportunity identification, but it can do definitely the constraint management and the molecular management. So it can suggest whether it's the molecular management until unless it is in a closed loop, which is the next item. Then the product blending optimization is also can be seen as one of the potential benefits of using this. Then we come to the real-time optimization. Here, the automatic implementation is the key, and so it captures the dynamically the constraints and the price movements. So it has autonomous operation, and site-wide implementation or unit-wide implementation, both can be done. It depends on the requirement and the purpose. And last is the automation. Automation is mostly on the other side, where you have the product evacuation and also the shift reports and generating different kinds of report, sustainability, streamline of the workflow, and utilization of resource. So these are some of the aspects we call it a value proposition. Now, what are the tools we typically use for development of advanced analytics? So mostly some of them are based on first principles, and they are detailed models which use them. We already use, every refiner is using them for unit monitoring or equipment monitoring. Now the kinetic model and equilibrium based reactors are also there, rigorous towers. Then we have the process digital twin. They basically focus utilizing the simulation capabilities, and that gives a deeper analytics than the raw value or the measured value. Deployment is generally supported by the KBC consulting group in this aspect. Now, opportunity identification for margin improvement, as we have already talked about. Focus on the ways to realize the benefit. So that is one of the key focus we always have, how to realize the benefit out of it. And benefit sustainment through dashboard and profit tracker. These are very important part actually to sustain the benefit. So this also gives the confidence on the operating companies to deploy this model in a closed loop. Before having the closed loop, have a digital twin is always a good thing. Now we talk about the closed loop optimization with real-time optimizer. This is being already part of the industry for since few years now. And the integration also generates the accurate inferentials, and we can calculate the gains of the APC also. The optimum trajectory reduces the time and achieve how quickly you can achieve the optimum operation. That is one part of the also of the RTOs. Segregation of steady state determination and optimization. This is a proposition KBC has. So segregate these two stages, and can be applied on an asset or a unit or an entire refinery. That depends on the purpose of the client. And lastly, on the integration with AI/ML. So this integration, the platforms provide the flexibility to have plug in with the different platforms which have using on the AI/ML engines. And various use cases have been identified. I will also touch upon some of them in the subsequent slides. Monitoring of model health, that is also key area we are focusing. Now, after the brief introduction, I will just go into the part of digital twin. So essentially, what are the value propositions? We have already discussed some of them. So identifying an improvement opportunity, that is one of the, and sustaining that improvement opportunity and identifying the gaps. So this is the part of profit improvement. And then KPI management, and then model assurance. Under the model assurance, we also focus on the LP model assurance and simulation model assurance, both. And data reconciliation, that is a very important part actually in a process industry to do data reconciliation. Now, data reconciliation in our platform, we do it with the elemental also, like sulfur balances and the nitrogen balance. And so that gives you quite a different picture than just closing the mass balance. And also the single source of truth. So that is also the effect of the visibility and the visualization through the digital twin. And collaboration. So these all things leads to collaboration through the organization. About the KPI management, there are various KPIs, so we can calculate them. And there are some, these are generally agreed in advance when we start the project and must be quantifiable. So all KPIs, either intrinsic or non-intrinsic, everything has to be quantifiable. A KPI from plant measurements are typically feed rate, product qualities, and also the yields and other pressure temperatures. Fractionation efficiency is also kind of based on the lab analysis and the analyzers. And there are intrinsic KPIs. So these are very important part in generating the confidence. And these are like column flooding, exchanger UA, and fouling factors, coking rate inside the tubes, and the cyclone velocities, things like that. So these actually drives the operator confidence, and they help maximizing the asset utilization. How do we use the digital twin for improving the profit? So this is one of the things. So there are various ways and inputs we get. How do we get collect the data about the unit and the process and the constraint? Essentially, they go through the screening process. This is not an automated process by itself. But once you identify any opportunity, digital twin allows you to quantify the lost benefit. It allows you to have a digital rigor on an autonomous basis, which drives the profitability sustainment actually. So if you see the identification, screening, techno-economic evaluation, implementation, and benefit sustainment. So these are the parts where digital twin can play a role at different levels. There are few aspects on this LP model health and the process simulation model health checks. So the trend below actually shows the kind of models. It actually gives you the trending of all three aspects together. So that gives you the visibility whether your LP model or your simulation model is in line with your expectation or not. Is there any deviations? And subsequently, I will also talk about what a model can do autonomously also, whether to, apart from tracking, it can calculate and correct itself. So this is the typical architecture. This is a very simplified version of architecture. So you have the historian data and the LIMS data. They are coming essentially from DCS. Then you have the process simulators as a digital twin replica of your asset or unit. And subsequently, in the below, we have different levels of calculations or different requirements. So some are process models, some are monitoring services, some are LP submodels and their calculations, and KPI estimations. So everything can go into the database. So there are some abbreviations. DQP is basically data quality parameters. MPI is a model performance parameter. So these things essentially get stored. They can be put into dashboard for better visibility or helping the client, and also put in the ERP system or in our KBC Explorer. That also worked as the similar purposes. Now we'll talk about the digital dynamic real-time optimizer. This is a product we are working already with our parent company Yokogawa and KBC. So here the concept is, as you see from the process, there upper layer is the DCS, then the APC, then the optimizer, and then the operator. Now here PetroSim or the digital twin play a part in the before the optimization loop. It essentially generate the gain matrix, and it is a steady state simulator. However, it can generate a gain matrix, and optimization happens at the software called PACE, that is Yokogawa software, and on that layer it happens optimization, and optimization then being implemented through the APC to the DCS. So the frequency of optimization is high compared to other conventional RTO suppliers. So there are some typical differentiation. What we differentiate from the traditional RTO to dynamic RTO is, traditional RTOs basically deploy on the, it has to wait for the steady state to achieve in the system. Optimization is not performed, cannot be performed without the detection of steady state. And the same model is used for detection of steady state and also for the optimization. So essentially it makes the complexity, it increases the complexity of the model. For the dynamic optimization, the key part is optimization is being performed outside the simulation or digital twin environment. And it doesn't has to really wait till the dynamics have steady state, stabilize everything. So it is easy to maintain. And these are the level 2. So I am short on time, I think. So this is the AI ML aspect. So this is used for model upkeep. So essentially the models on its own and the reactor models require a calibration. So kinetic model, so AI can detect when the model is deviating, and it can correct itself, suggest and the correct itself. So these are the typical applications. We are having this as a service-based thing. So
Wonderful, Dipankar. I think this
thanks.
was really very
Sorry.
helpful in the interest of time, but very insightful, very deep.
Yeah.
We are pretty sure like this topic cannot be covered within 1 hour. I think thanks for bringing the insight.
Yeah.
I will now request Dr. Mitra.
Let him conclude.
Yeah, can you just
Quickly,
conclude?
very
Yeah.
quickly.
Okay, thanks. Thanks for that. So it is typically, I will just talk about a ML part. So this is the way some of the typical aspects of the machine learning we see against. So it is being presented in a comparative manner on a first principle against the machine learning. So it is not really against, but it is some of the points which can be covered more by machine learning. Some. So what we suggest essentially on the process domain, chemical engineering, and suggest we can go by first principle models, and wherever there is a gap in the identification or understanding, that gap can be filled by machine learning. And in the subsequent slide, we talked about the strategies how to implement the machine learning. So essentially the first step is to have the first principle based understanding of the model, and then find the gaps. What are the gaps which our existing.
Conclude.
Okay.
Thank you.
Yeah.
Thank you,
Thanks.
Dipankar.
Thank you.
Round of applause, please.
I think in this session 44, um, um, there were a multiple set of topics, but the key takeaway is that the Indian R&D in the chemical refining and petrochemical sector has come of age. So there was an excellent thing on by Hindustan Petroleum on propane dewaxing additive, which I think is brilliant, and it can be applicable to other edible oil industry, which will be very, very good for Atmanirbhar Bharat. Also, lubes will always continue even after the ICE to EV transformation. The other is the single step DME. Actually, it gives a great way to substitute LPG in our country, and so, but it is not recognized so much yet. The other two are related to modeling and optimization and digital twins, and especially when these our refineries are getting more complex from COTC. I think the EIL presentation of a single network model is actually path breaking. And of course, digital twin by KBC is brilliant. So at the end of the day, we are developing technologies, not only process technologies, but also digital technologies, and that's brilliant. Thank you.
Thank you, sir. Thank you, Dr. Mitra. Thank you, everyone.